This is part of the BocaPhysics mini course on nuclear physics. In today's lecture, I'm going to discuss radioactivity, in particular the exponential decay law. So I'll be deriving the exponential decay law and working through 5.5 examples. So let's go back to the late 1890s. Briefly. And Henri Becquerel was working with uranium salts. And what he observed was that these uranium salts emitted radiation, but it was a different kind of radiation. This radiation could actually pass through black paper. So he termed this radioactivity. A few years later, the husband and wife team of Marie and Pierre Curie identified 3 radioactive elements. Polonium, radium, and thorium. And it was also observed that this kind of radiation could be classified further. It behaved differently. So Ernest Rutherford, the same physicist who identified the positively charged nuclei inside of atoms, classified this radiation into 3 kinds. Alpha, beta, and gamma. So alpha penetrates the least distance, so it can even be stopped by paper. Beta rays travel a little further, but they can be stopped by a few millimeters of metal. And gamma rays penetrate furthest. What are alpha, beta, and gamma rays? To be more precise, alpha rays are basically twice ionized helium atoms, or they're just helium nuclei. Beta rays are just electrons or positrons. Positrons are the antiparticle counterparts of electrons. So they have the same mass, but they have opposite charge. Gamma rays, basically they're just photons, but with very high energy. And the energies go up to about 10 mega electron volts. In upcoming lectures, I'll be discussing how these decay processes occur. So in other words, you've got a radioactive nuclide. What does it decay into, and what can it decay into? So those questions I'll answer in an upcoming lecture. But for now, just know that they're alpha, beta, and gamma, and these 3 kinds of processes can be described by the exponential decay law. Also, elementary particles that are unstable decay in this same fashion as well. Essentially, any kind of unstable quantum state can be described by the same decay law. Since we're talking about quantum theory, it means we're talking about probabilities. Okay? So what I mean by that is if I've got a radioactive nucleus, I cannot say with certainty after a certain amount of time it's going to decay away. I can only speak of a probability that a decay will occur. So let's quantify what I mean by that. just writing this on the board to drive home the point. Cannot be said with certainty that an unstable nucleus will decay after a certain length of time, only if there's a probability that it will decay in a certain time interval, okay? And why is that? Well, to put it in, I guess, kind of a casual way, is that the unstable nucleus doesn't know how long it is that it existed. So for this reason, we're going to introduce a quantity called the decay constant. And let me just say this before we go on. You want to think about a coin toss, okay? You toss a coin, you've either got heads or tails. It's a 50-50 chance. Well, let's say you toss a coin one time. It turns up heads, okay? Toss a coin the second time. What's it going to be? You say, oh, gee, it's 50-50, so therefore the next time it has to be tails. Now, there's always going to be a 50-50 probability it's going to be heads or tails each coin toss, because the coin doesn't have any prior knowledge of how it behaved. So in the same way, a nucleus doesn't know how long it's existed. So we can only speak of probability. So our decay constant, lambda, really is the probability of decay in a certain time interval. So that has units of inverse. Inverse time. So let's say we have some radioactive nucleus, or let me say unstable nucleus. There's a 4% probability that unstable nucleus will decay in the upcoming year. In this case, lambda is equal to 0.04 inverse years. So let's say I know for certain this unstable nucleus was just formed. Okay, and 1 year time interval, there's a 4% probability of decay. Now let's suppose I have an unstable nucleus of the same kind, and I know it's been around for 10 years. What's the probability that that unstable nucleus will decay? It's still going to be 4%. Why? Because the unstable nucleus has no knowledge of how long it's existed. So we're just speaking of probabilities of decay occurring over a certain time interval. So with that, let me define or rather write down an expression for the rate of decay. Now we don't just have a single nucleus, we've got a whole sample of a certain kind of radioactive element. And let's say the rate of decay we'll write as a capital letter R as a function of time is equal to the decay constant, the probability of decay basically, times m of t, which is the number of particles at time t. Okay? It is also true that the rate of decay is equal to minus the time derivative of the number of particles. So if I combine these right-hand sides, and leave off the argument t for brevity. So we have the whole derivative of the number of particles with respect to time is equal to minus lambda times n. And also, just one more point, depending on the textbook that you consult, some authors use the character lowercase r to indicate decay constant, and other people use different notation. But most people use lambda, but just be aware, this has nothing to do with wavelengths. This strictly is the decay constant, okay? So this is a first order linear differential equation, and we're going to combine like terms on each side, so this becomes dn over n is equal to minus lambda dt. When we integrate from some time, when I integrate from time 0, and at time 0, I know that I have n naught nuclei, and I go up to some future point in time, time t, and we'll just call that n. So to do the math here, this integral is just going to be natural log of n evaluated from the initial number of particles up to some final number of particles, and minus lambda t. So on the left-hand side, that's natural log minus natural log of n naught. Well, one of the properties of natural logs is that if you have the difference of two natural logs, that can be written as natural log of n over n naught is equal to minus lambda t. And I want to solve for capital N here, so I do that by taking the exponential of both sides. And remember, another property of exponentials and natural logs. So I take e to the natural log of x, that's just equal to x. Write a big E under each of these. So this becomes n is equal to n naught e to the minus lambda t. And that's your exponential decay law. Gives the total number of particles at some future point in time based on how many particles there were initially, and also according to how whatever substance it is you're looking at decays. And that's, that quantity has to do with the kind of nuclide you're talking about. So it's n is equal to n naught e to the minus lambda t. Okay? Now another useful quantity is the so-called mean time. And that is defined as 1 over lambda, and obviously it has units of time. If I plug this into my exponential decay law, see if I evaluate the number of particles at the mean time. And basically that's the amount of time it takes the total or the original number of particles to decay to 36.8%. So 6.8% of the initial number of particles. So that's one useful way of writing the exponential decay law. That's the mean time. What's more familiar probably to most people is the half-life. And you talk about half-lives more frequently in nuclear physics. Particle physics, people talk usually in mean lifetimes. So what's the half-life? Well, that is the time it takes for the number of particles, or half the number of particles, to decay. And I'll put a little subscript on T to indicate that. So I'm going to go ahead and rewrite this. Lambda in terms of the half-life and vice versa. Again, it's I'm going to solve for t to the half-life in terms of lambda, and I also want to write lambda in terms of the half-life as well. But anyway, I'm going to take the natural log of both sides, so we have the natural log of 1/2. And that's equal to the natural log of e to the minus lambda t 1/2. So again, you take the natural log of an exponential. That's just equal to minus lambda t 1/2. And natural log of 1/2 is equal to minus natural log of 2. That's another property of the natural log. Okay, so therefore t 1/2 is equal to natural log over the decay constant lambda. Or what's going to be more useful for us is to write it the other way, solve for the decay constant in terms of half-life, because half-life is what's noted in the nuclear data tables. So that's natural log of 2 over t 1/2. Okay? So what have we done so far? We've derived the exponential decay law. We've discussed what is meant by the term mean life or mean time rather, and we've also defined what is meant by the half-life and written the decay constant in terms of the half-life. So, as I mentioned, this is one way of writing the exponential decay law. I'm going to show you another way of writing it. I'm going to go ahead and substitute in this lambda written in terms of the half-life in here. Okay, so my exponential decay law now becomes a naught e to the minus natural log of 2 times t over t to the 1/2. And just write this a little differently to make it clearer. Okay. Now, another property of natural logs is if you have, say, the product of some a times n natural log of b, that's the same thing as natural log of b to the 8th power. So this is actually n naught e to the minus natural log of 2, or let's put natural log of 2 to the minus t over t 1/2. Now, exponential of a natural log, this just becomes n naught times 2 minus t over t to 1/2. And writing it a little differently, n naught over t2 to the t over t to the 1/2. If I define n to be number of half-lives, so n is equal to t over t to the 1/2, this just becomes n naught over 2 to the n. So it makes it clear what's meant by a half-life. After one half-life, the number of particles decreases to 1/2 from what was there initially. In 2 half-lives, it becomes 1/4, 3 half-lives, 1/8, and so forth. Okay? So this is your second useful form of the exponential decay law. And let me just leave this up here for a minute, because now we're going to work through some examples. example that I'm going to work through involves the radioactive element, radon 222, and I've made the number of protons explicit there. So let's suppose initially there are 1,000 nuclei. And I want to figure out or answer 3 questions. How many nuclei do you expect to remain after 5 days? And what's the rate of decay initially? And after 5 days. And finally, what's the probability of decay after 5 days? And that's, of course, of the remaining radon nuclei. So first order of business, you want to consult your table of nuclear data, and if you look it up for radon 222, you'll find that that has a half-life of 3.82 days. And you want to point out, depending on what source you consult, you will most likely see discrepancies in the least significant digits, especially if you're looking at an older textbook and comparing it with data from the Nuclear Data Center. So anyway, I'm just using 3 significant digits here, and 3.82 days. So what are we going to calculate first? We should calculate the decay constant. So lambda is equal to natural log of 2 over T1/2. And that's equal to 0.181 inverse days. To answer the first question, how many nuclei remain? Well, I'll just plug it into the exponential decay law. So that's 1,000 nuclei times e to the minus 0.181 inverse days times 5 days. So you'd expect 405 nuclei of radon 222 to be there after 5 days' time. Now, to answer the question, what's the rate of decay? Well, initially, rate at time 0 is equal to probability times the number of nuclei there originally. So this is equal to 0.181 inverse days. So you'd expect there to be 181 decays per day. And after 5 days, rate of decay would drop to 73 decays per day. So it's an exponential decrease in the number of particles and also drop in the rate of decays as well. To answer the third and final question, how does the probability change after 5 days? Initially you had 1,000 nuclei sitting there in a sample box or whatever. And then after 5 days of time, how does the probability change? Well, the answer is it remains the same. Remember, it doesn't matter how long those radon 222 nuclei have existed, there will always be the same probability of decay. Okay? Let me just leave this solution up at the board just for a minute before we move on to the next example. Okay, so the next example I'm going to look at is plutonium-244. And let's suppose initially I have a sample consisting of 2 grams of pure plutonium. Let me answer 2 questions. How many nuclei remain after 1 half-life? And after 2 half-lives? And number 2, what's the rate of decay after 1 half-life? And after 2 half-lives? We can consult a table of nuclear data and look at the mass, atomic mass of plutonium. And that is equal to 244.064205 atomic mass units. Again, if you consult a different source, you'll most likely see a discrepancy in the least significant digits. For our purposes, just doing these problems and boards, not a big deal. Of course, if you were actually in the business of, I don't know, you're a nuclear engineer, you want to consult an authoritative source, and the best place to look is the nuclear data center. Okay. So let's see, that's the mass. Do I need anything else? No, I do not. Okay, calculate the number of atoms, and basically it really is we're after the number of nuclei. It's the same thing. We've got 2 grams of plutonium, and I know that there are 244.064205 grams per mole. And there are 6.022 times 10 to the 23rd nuclei per mole. And I do want to emphasize, we are really looking at the atomic mass because that's what's listed in the tables. So obviously you've got this number of atoms, you've got the same number of nuclei, okay? So this is 2 over 244.04205. Times Avogadro's number. And we've got 4.93 times 10 to the 21st nuclei. So the question is, how many nuclei will remain after one half-life? Well, the easiest way to do that is to use this second expression for the exponential decay law. One half-life, you're going to have half of the, you'd expect half of the nuclei to still be there. After 2 half-lives, you'd expect there to be 1.23 times 10 to the 21st nuclei. So half, fourth. Now to figure out the rates of decay after one half-life, well, that's just probability of decay times the number of nuclei that remain after one half-life. Well, lambda, let's see, we can just maybe put it up here. Lambda is equal to natural log of 2 over t to the 1/2. Half-life of plutonium is 80 million years. Or 8 times 10 to the 7th years. Therefore, decay constant is equal to 8.66 times 10 to the minus 9th years. And if we want to put in a little bit more convenient term to specify this in units of inverse seconds, that's equal to 2.75 times 10 to the minus 16th seconds. So, rate of decay that means after one half-life, will be 6.79 times 10 to the 5th decays per second. And then after 2 half-lives, follow exactly the same procedure. That's equal to 3.38 times 10 to the 5th decays per second. So let me just leave that up on the board for a minute before we move on to the next example. let's next consider, we have a sample of an isotope of barium. And let's say in particular you've got barium 140 and we've got 1 milligram of that sample. So I want to figure out how many nuclei remain after, well, let's say 40 days. Well, you're given the amount in terms of grams, and you're also told how many days after you collect your sample. You want to see how many remain after that time is transpired. So you really can consult a table of nuclear data, and from that you'll see that the half-life of barium 140 is equal to 12.75 days, and moreover, its atomic mass is equal to 139.910605 atomic mass units. So the number of nuclei initially we got 1 milligram, so that's 0.001 grams. And furthermore, there are 139.910605 grams of this species in a mole. And we also know that there are 6.022 times 10 to the 23rd nuclei in a mole. So there will be 4.30 times 10 to the 18th atoms and, well, and hence nuclei in your 1 milligram sample of barium 140. Okay, so the question is how many nuclei remain after 40 days? So I'm just going to use the first expression of the exponential decay law. So that's 4.30 times 10 to the 18th nuclei times e to the minus, and we need to calculate the decay constant. We'll do that next. That's equal to the natural log of 2 over t1/2. Which is equal to 0.05436 inverse days. Just let me repeat, that's 4.30 times 10 to the 18th nuclei times e to the minus 0.05436 inverse days times 40 days. And do the math, we will wind up with it'll be 4.88 times 10 to the 17th nuclei. Just leave this up here for a minute before we press on. Okay, so let's suppose we've got a stockpile of 1 kilogram of uranium. And I want to know after a billion years how many uranium nuclei remain? And I'd also like to know the rate of decay. And I should emphasize that this is a terrestrial source. In this case, you have to take into account that there are different isotopes of uranium because of the way the question is posed. You see, naturally occurring uranium can either occur as the isotope U-234, U-235, or U-238. U-234 accounts for only 0.0054% of natural uranium. U-235 accounts for 0.7204%, and U-238 accounts for 99.2742% of your source of uranium. So because U-234 has so much smaller abundance, I'm just going to ignore this for the present calculation. And instead focus on U-235 and U-238. Now, just FYI, U-235, if you're interested in fueling a nuclear reactor, that's the isotope that you want to use. And again, we'll get into nuclear reactors a little bit in an upcoming lecture. Okay, so the best approach to take here is to create a table. So we've got U-235 over here. And U-238. So we'll look up atomic mass. And half-life. And we want to calculate decay constant, and how many nuclei initially, and after 1 billion years. And finally, the rate of decay after a billion years. Make sure I don't leave anything off here. No, I did not. Okay, so our atomic mass for U-235 is equal to 235.043930 atomic mass units, and for U-238, 238.050788 atomic mass units. Now the half-lives are 704 million years for U-235. And for U-238, it's 4.468 times 10 to the 9th years, or 4.468 billion years. Okay, so let's calculate the decay constants. So in this case, we just write it off to the side. This is just as the form of natural log of 2 over t to the 1/2. To calculate how many nuclei there are initially. Well, I think I'll write in the block here. And use after the rate of decay here and the number of nuclei here. This is going to be n naught minus e to the minus lambda t, and then the rate of decay is going to be equal to lambda times number of nuclei after a billion years. Okay, so let's plug everything in and do the math. The decay constant for U235 is 9.85 times 10 to the minus 10th inverse years. And for U238, it's 1.55 times 10 to the minus 10th inverse years. So how many nuclei initially? Well, we've got 1 kilogram stockpile of uranium. So that means the mass of U235 is going to be equal to 7.204 grams. And I almost did not give myself enough room. Let me just read this out. This will be 7.204 over 235.043930 times Avogadro's number 6.022 times 10 to the 23rd. Initially, there are 1.85 times 10 to the 22 nuclei of U235. Let me go through an identical calculation for U238. There are 992.742 grams of U238 in your sample initially. Divided by 238.050788 times 6.022 times 10 to the 23rd. So there are 2.51 times 10 to the 24th nuclei of U238 initially. Now, to answer the question, after 10 to the 9th years, well, we need to start out with the number of nuclei available initially and multiply by e to the minus lambda t. Now, since I'm kind of running out of space here, I'm just going to do the calculation and write the answer in the appropriate space. So here, this is for U235 will be 1.85 times 10 to the 22 e to the minus 9.85 times 10 to the minus 10th times the length of time, which is 1 billion years. And we're left with 6.91 times 10 to the 21 nuclei. Doing the same calculation for U238, we start out with 2.51. start out with 2.51 times 10 to the 24th nuclei times E to the minus 1.55 times 10 to the minus 10th times billion years, 10 to the 9th, and we'll be left with 2.15. Times 10 to the 24th nuclei. And last but not least, to figure out the rate of decay, we simply multiply the decay constant lambda times how many nuclei remain after a billion years. Again, I'm just going to write out the final answer here because things are getting a little bit crowded on the board. So this will be 9.85 times 10 to the minus 10th for U235 times the number of nuclei that remain. So the sample, billion years from now, is going to undergo 6.81 times 10 to the 12th decays per year. And then for U238, again, we'll multiply the decay constant, in this case 1.55 times 10 to the minus 10th, times the number of nuclei that remain after a billion years, or 2.15 times 10 to the 24th, and that is 3.33 times 10 to the 14th decays per year. Now, in each of these cases, you might want to express this in decays per second. In that case, that's roughly 216,000 decays per second. Here, remember to convert, you're just going to divide by 365, 24, 365 days, 24 hours in a day, and 3,600 seconds in an hour. That would be 1.06 times 10 to the 7th decays per second. Okay? And that is how the behavior of these two isotopes of uranium compare. Okay? Let me just leave this up here a minute before we move on to kind of a side problem related to U235 and U238. Okay? Now, there's another interesting problem that you can work regarding U235 and U238. It's believed that those two isotopes of uranium were formed in a supernova explosion. So, let's say that initially there was the same amount U235 and U238, but because they have different decay constants, this is why there's so much less U235 naturally available right now than U238. So what I'm going to do is write down the exponential decay law for each of these isotopes separately. The number of nuclei of U238 is equal to N naught times E minus lambda T, and again, subscripts indicating we're referring to the isotope U238. And we have a similar expression for U235. Now, we're going to suppose that initially there was the same amount of U235 and U238. So that means that these two quantities are equal to each other. So why don't I just drop the reference to the isotope in question? we divide this first equation by the second. So you have the ratio of the number of particles, U238 to U235, and that's equal to e to the minus lambda 238 minus lambda 235 times time. I want to solve for time. I want to figure out how much time has transpired leading to the present abundances of U235 and U238. So I'm going to take the natural log of both sides. We just calculate the decay constants for each of these isotopes, and for lambda 235, that's equal to 9.85 times 10 to the minus 10th inverse years, and for U238, and it's equal to 1.55 times 10 to the minus 10th inverse years. 4, time is equal to natural log of 238 over 235. And instead of using numbers, particles, we're going to use the abundances. So it's going to be 99 .2742 over 0.7204. That's roughly equal to 5.9 billion years, which tells you when these isotopes were formed, and hence roughly the age of the Earth. So that's 5.9 billion years. We just leave that up here for a minute before we press on to the final example of this lecture. The last example that I'm going to work through today has to do with radiocarbon dating. And the procedure is that you measure the activity of a certain sample, and from that you can go backwards and determine how long ago it was produced. Well, how this procedure works in more detail is that every living thing absorbs carbon. Most carbon is in the form of carbon, the isotope carbon-12, and it's roughly 99%. Actually, it's a little bit less than that. Another stable isotope of carbon is around 1% of all naturally occurring carbon. Now, there's another isotope of interest, and that's carbon-14. This one is radioactive. has a half-life of 5,730 years. Carbon-14 is continually produced in the atmosphere via collisions between cosmic rays and nitrogen. So by that process, carbon-14 is produced. It's got a half-life of 5,730 years. And every living thing absorbs carbon, whether you're talking about animal or plant. So every living thing is absorbing carbon-14. Now let's suppose that you're an archaeologist and you've come across a wooden statue. And you take a little sample, and you probably would take this much. Well, let's suppose you've got a 10-gram sample. And you've determined that the rate of decay, or activity I should say, is around 70 decays per minute. So knowing how much sample you have and the activity, you can determine how old it is. Well, the first order of business is to figure out how many carbon-14 atoms were initially present in that statue, or actually initially present in the tree from which the statue was made. So initially, and by the way, I'm assuming that the statue just has carbon-12 atoms in it and also just a carbon-14. Well, 1.3 out of 10 to the 12 carbon atoms are carbon-14. So I'm going to multiply this by 1.3 times 10 to the minus 12. That's the portion of carbon-14 that was initially in the wood that made the statue. And this times 6.022 times 10 to the 23rd. Atoms per mole. So initially there were 6.53 times 10 to the 11th atoms and hence nuclei of carbon-14. So initially the rate of decay was equal to lambda times n naught. Now I haven't calculated lambda, I'm going to do that right now. Lambda is just equal to natural log of 2 over t 1/2. So in this case, the half-life of carbon-14 is 5,730 years. Which means that the decay constant is 1.21 times 10 to the minus 4 years. And there were initially 6.53 times 10 to the 11th nuclei available. But I've expressed the initial activity, or rather the activity, presently as in terms of decays per minute. So I'm going to convert this over by dividing this by the number of days, 365, the number of hours in a day, and the number of minutes in an hour. initially, when this tree fell over, struck by lightning, who knows what, and our prehistoric woodsman or craftsman came along and decided to make a nice little statue. The activity of this was 150 decays per minute. Now it's presently 70 decays per minute. So I get the rate of decay presently in terms of what it was initially. I'm going to invert this expression, and once again, I did not give myself enough space. Let me just write it in here, this little box here. So we have R of t over R naught is equal to e to the minus lambda t. I'm going to take the natural log of both sides. So natural log of R, I'm just going to leave off the argument, is equal to minus lambda t, and therefore t is equal to minus 1 over lambda natural log of R over R naught. And that is equal to minus 1 over 1.21 times 10 to the minus 4 years inverse natural log of 70 over 150. And I wind up with a time of roughly 6,300 years. So it's been 6,300 years since our prehistoric craftsmen went out into the forest, either cut a tree down, found a tree that was struck by lightning, whatever, carved a nice little statue, and now 6,300 years later, here we are. Here your archaeologist is looking at the statue. So that is how you do radiocarbon dating. Now, oftentimes if you're on a road trip somewhere, you're out in the great outdoors, and you stop at a site, say in Canadian Rockies, and they'll list the ages of the rocks. And you might be wondering, well, now how can they list the ages of the rocks? How can they figure that out? That some formation is billions of years old. They're certainly not using radiocarbon dating because it's obviously not living. And furthermore, the half-life is 5,730 years. So radiocarbon dating is really only accurate up to 50, 60,000 years. What they're going to use instead, and potassium-40 has a half-life on the order of about 1.3 billion years. So that concludes today's lecture. Next time around, we'll get into discussing what happens with alpha, beta, and gamma type decays.